Hi everyone, my name is Shalef Shire and I will introduce you to our work Model X sequential testing for conditional independence via testing by betting, a joint work with Gal Mammon and Yaniv Romano. In 1990, the first ever complete sequencing of the human genome began, which took 13 years to complete and came with a staggering price tag of around $2.7 billion. Fast forward 30 years later and the DNA sequencing process takes just about 5 hours to complete and costs approximately $1,000. This advancement demonstrates the amazing abilities we have today to collect, store, and process data. In our example, this data is the secret sauce of humanity. We now have the opportunity to dare and ask intriguing questions to better understand the human genome, genetic diseases, and more. Indeed, modern scientific research is driven by data, where the common research paradigm is to collect data first and ask questions later. However, with the increasing affordability of the data acquisition process, the desired paradigm is to ask questions online as the data is being acquired. This introduces great statistical and machine learning challenges. One outstanding challenge is overfitting. If we will torture the data enough, it will confess and say whatever we want it to say. In this talk, we focus on sequential testing for the conditional independence problem, where we collect samples of features and the response under study, and our goal is to test online whether a specific feature is associated with the response after accounting for the effect of many other features. I will define it formally next. Importantly, the desired sequential test should possess two crucial properties. Firstly, it should have the ability to perform sequential testing for conditional independence while ensuring reliable and accurate results. Secondly, it should enable the termination of data acquisition as soon as statistically significant results are detected. This early stopping attribute is particularly crucial in scenarios where ethical considerations need to be taken into account, for example in clinical trials. Let me now formally define the online conditional independence testing problem. Suppose we have a sequence of independent and identically distributed samples from a joint distribution Pxyz. Here Y represents the response under study, X represents the feature of interest, and Z denotes a vector of other features. Our objective is to test the null hypothesis that Yt is independent of Xt given Zt for all time steps t. In simpler terms, we want to determine whether Xt provides additional predictive power on Yt beyond what is already known from Zt for all time steps t simultaneously. We say that if x, y, z satisfy the null hypothesis, then x is an unimportant feature and x is important otherwise. To provide a concrete example, let's consider a real-life scenario. Suppose our feature of interest x indicates the presence or absence of a specific HIV mutation in a treated subject, z represents a vector of other HIV mutations, and y represents the measured resistance that the subject has developed to a particular medicine. The objective here is to determine whether a particular mutation affects drug resistance given the effect of the other mutations. This question is of immense interest as it could potentially lead to the development of improved drug treatment, for example. Moreover, since we are dealing with patients, ensuring reliable conclusions and supporting early stopping is of utmost importance. Our proposed sequential test for conditional independence was inspired by two main ideas. The first is a conditional randomization test, the CRT, proposed by Candace et al., which is an offline test for conditional independence that does not support online monitoring and early stopping. The second concept is the testing by betting framework initiated by Schaefer and Vovk, which has gained popularity recently. I would also like to mention the concurrent work of Grunwald, Henze, and Lardy, which was inspired by similar ideas, but ultimately resulted in a different but related sequential test. I now turn to describe our proposed online test for conditional independence, and I will begin with a preview of our method to gain intuition. So imagine a game in which we have an initial toy money S0 of 1. Next, we acquire a new data point xt, yt, zt, and based on our prior knowledge and the new observation, we place a toy money bet on how we believe that x is important. The more we have confidence, the more toy money we may bet. The next step in our method is to uncover the truth about the importance of x. Note that this is the most challenging aspect of the test, as we do not have any knowledge of whether x is important or not. For the time being, imagine we have such knowledge. Of course, I will elaborate later on how we can determine the truth without directly knowing it. After knowing the truth, we can conclude whether our bet was correct or not. If we won the bet, we increased our wealth ST by the amount of money we risked. If we lost, we decreased our wealth by the same amount. The final step is to check whether our accumulated wealth has surpassed a predetermined level. If it has, we can confidently conclude that the tested feature is significant and terminate the testing process, knowing that the type 1 error rate is controlled. However, if we have not yet reached that level, we repeat the process. The intuition behind this procedure is that if the null hypothesis holds, meaning that x is not important, we should not be able to increase our wealth by betting against it. However, if our wealth does increase by betting against the null, then it is likely that the null hypothesis is not true, which means we can conclude that x seems to be important. Here we can observe the preview of our proposed method in action. The blue curve shows the wealth accumulated by the test when applied to simulated data, where x is not important, which stays low as expected. On the other hand, the green curve corresponds to simulated data where x is important. In this case, the wealth increases as we gather more data, eventually exceeding the predefined nominal level. Now that we've gained some intuition for the proposed test, let's move on to formalize it. So recall that our test starts by initializing the wealth process as 0 to 1. Then, for each new sample xt, yt, zt, we do the following steps. The first step is to generate a dummy feature x tilde by sampling from the conditional distribution px given z. The main reason to generate the dummy this way is that if the null hypothesis is true, then the original triplet xt, yt, zt is equal in distribution to the dummy triplet x tilde, y tilde, z tilde. In other words, if x is important, it is impossible to distinguish between the original and dummy triplets. Here we inherit the assumption that px given z is known or well estimated, which is not a weak assumption. In the paper, we elaborate on scenarios where this assumption makes sense, and a comprehensive discussion can be found in the original paper of CRT and Model X knockoffs by Candes et al. The second step is to compute an importance score WT that quantifies the importance of xt. One way to do so is to take a predictive model f hat t that was trained on previous data and evaluate the difference between the squared error evaluated on the dummy triplet and the one evaluated on the original one. The intuition is that if x is important, by replacing x with its dummy version, the error of f hat t should be higher than the error when using the original x. Importantly, if x is not important, then the expectation of wt given previous data equals to 0. This leans on the idea of the impossibility to distinguish between the original and dummy triplets when x is not important. In the next step, we bet money against the null. Here v, a bounded scalar between 0 to 1, is the ratio of the wealth that we are willing to risk. Next, we apply our betting strategy by updating our wealth using the importance score WT and the money we bet T. If our bet was correct, meaning that WT is greater than 0, then our wealth increases by multiplying it with a factor greater than 1. On the other hand, if our bet was incorrect, our wealth decreases by multiplying it with a factor smaller than 1. This design has a key property. If the null hypothesis is true, then the expectation of ST given previous information is ST minus 1, which means that our wealth process ST is a non-negative martingale. However, if the alternative hypothesis is true, There is nothing limiting our Wells process from growing. Lastly, if the value of our Wells process ST exceeds the predefined threshold of 1 over alpha, where alpha is the level of the test, we reject the null hypothesis and stop the test. If the Wells process hasn't exceeded the threshold, we continue to the next data point. As mentioned before, since our Wells process is a non-negative martingale under the null hypothesis, Wills inequality states that under the null, the probability of ST exceeding the threshold given previous information is bounded by alpha. Therefore, the probability of making a type 1 error is controlled by the level of the test alpha, which ensures the validity of our proposed test. To showcase the effectiveness of our proposed test, we conducted experiments with simulated data. We generated a sequence of samples by sampling ZT from a multivariate normal distribution with a dimension of 20. Then we sampled XT from a normal distribution where the mean is a function of ZT. Finally, we sampled YT from a normal distribution where for the non-null data, the mean is a function of both XT and ZT, and for the null data, the mean is solely a function of ZT. That is, X does not affect directly on Y, even though it is correlated with Z. As benchmarks, we use CRT and HRT, an efficient version of CRT, which are offline tests that are not valid in sequential testing without modifications. To adapt CRT and HRT for online testing, we employed AISTATS spending, a state-of-the-art alpha spending method developed by Tian and Ramdas. We set the level of the test alpha to be 0.05 and we evaluated the empirical power and type 1 error over 1000 independent trials. The left panel of this graph shows the type 1 error of the online methods as a function of the time step t. It can be observed that the type 1 error for all methods is below the level alpha. On the right panel, the empirical power is displayed, and it is clear that our proposed test in green achieved higher power than the online AISTATS CRT and AISTATS HRT tests. Interestingly, it also outperformed the offline HRT test and demonstrated competitive power to the CRT test. This slide shows histograms of the stopping times of our proposed test and the AISTATS CRT. The stopping time is the time step at which the test rejects the null hypothesis. The histogram demonstrates the distribution of the stopping times over 1000 trials. The y-axis represents the number of trials and the x-axis represents the stopping time. As can be seen, our proposed test stopped earlier than the AISTATS CRT, indicating that our test is more data efficient. To conclude, we introduced a novel online test for conditional independence that offers safe testing with early stopping and allows for any relationships between the response and the features. The test also incorporates online learning to effectively detect violations of the null hypothesis. Topics that I did not cover in the presentation but are covered in the paper are clever betting schemes, proofs that our test achieves power 1 if the model is accurate enough. This result is based on a recent work by Shekhar and Ramdas. More practical improvements for reducing algorithmic randomness induced by sampling the dummy features, and a comprehensive empirical study that includes experiments on simulated and real-world datasets. Thank you for your attention.